Hello and welcome to the sixth in my series of videos, all under the umbrella title of Absolute Relativity. And as I've said before, I hope you've watched the other videos, because the essence of this that I've called absolute relativity, and as we go on it will be more obvious. Eventually it'll be obvious why it's called absolute relativity, but what I'm doing is showing that subatomic particles, particularly electrons and photons, plus the Higgs boson, are not necessary to describe what's going on within an atom. Now I want to take this further on in this one by having a look at the Schrödinger equation. But before I do, a little recap of this neon atom, which is showing two, sorry, I'm supposed to follow that circle, which is showing two energy levels, two shells, N1 and N2, in which N1 because this is N1, L equals 0, so all we get are the two, and I'm saying now these are protons. These are effectively hydrogen atoms. They are ground level protons, ground level hydrogen atoms. So these two hydrogen atoms, now in the center of here, I'm saying what we have at the center around which all this is clustered, effectively moving, are these protons, these hydrogen atoms. And as I've said before, if you look at the periodic table, then you can see that everything is made up of protons and neutrons. All matter in the universe is made up of protons and neutrons. And the neutron is a proton with a bit of changed energy. You get a neutron out of a more complex atom, take it out on its own, it will, after a matter of minutes, communicate with another atom, change its energy to become a proton. So effectively all we have is protons. And then in N2, where L equals 0, minus 1, 0, plus 1, and we have these here revolving with, this was L equals 0, these ML are where these equal minus 1, 0, plus 1, and they're at a different energy. This outer level is at a higher energy than the inner one, and it looks as though everything on that shell is at the same energy. In fact, there would be a bit of a change of energy from these to these. and indeed from these two to this one, these two would be the same. And we'll discuss why, but I'm going to look further into that construction after we've had a look at the Schrödinger equation. And all we're going to do is to take a brief overview of the Schrödinger equation, which, given the wave function of a particle, describes the energy and momentum of that wave function. We're going to look at the time-independent Schrödinger equation applied to the wave function of a hydrogen atom. Time-independent. Schrödinger equation comes in time-dependent or time-independent. We're going to be using the time-independent rather than time-dependent, because the hydrogen atom can be represented as an oscillating particle in a three-dimensional infinite potential energy well. The well is the negative energy of the hydrogen atom itself, surrounded by the infinite potential energy of the rest of the world. In this way, the hydrogen atom is contained within this potential energy well. Sometimes it's called the particle in a box. It's contained within this potential energy well, described by the time-independent Schrödinger equation. And not until the hydrogen atom is ionized can it be found anywhere but within the well. The probability of finding the particle is calculated using the modulus of the square of the wave function, provided it has been normalized, what we call normalized. That is to say, its integration over an infinite distance is equal to 1, or 100%, confirming that the particle exists and must be found somewhere. I'm going to come back to that at some point. It must be found somewhere. I'm really interested in that, but that's for later on. Anyway, all of this information is available to anyone who wishes to study the Schrödinger equation, or it's understood obviously by anyone who has studied the Schrödinger equation. In this video, we'll have to assume a working knowledge, as all we're going to do is take a brief overview of the equation and its application to the hydrogen atom, and then see how the results apply to absolute relativity and its central assertion that all subatomic particles can be described as energy exchanges between protons or hydrogen atoms. So, we're going to go on now to look at the Schrödinger equation. By the way, I meant to say in the introduction that at the end of the last video, I suggested that in this video I was going to look at the Schrödinger equation and the measurement problem. I'm not going to do the measurement problem in this one. I'm going to do the measurement problem as a separate one after this. So, on to the hydrogen atom. Now, I've got a series of plates here, like presentation plates, so we can look through the information. If you want to, I'm going to buzz through them quite quickly, but of course, if you want to have a closer look, a longer look, all you've got to do is pause it each time. I'll give you, there'll be enough time to pause it, have a good look at it, and then carry on. So we're looking at the application of the Schrödinger equation to the hydrogen atom, a solution of the Schrödinger equation for hydrogen, and a quick look at quantum numbers. But we've done the quantum numbers in the previous videos. We've had a look at them, but we may just cover them again. So, as I said, we'll be looking at this as a three-dimensional infinite potential well, as I described, and the hydrogen atom can be described as, can be approximated as an oscillating particle in the well. So oscillating, as it were, like a swing. Imagine a swing. What we've got is potential and kinetic energy. This is what this would begin with, the conservation of energy here. Hang on a second. Conservation of energy here. K is kinetic energy, V is potential energy. It may not stay with V as potential energy as we go through. Some of the slides say something different, but so you imagine the swinging backwards and forwards. When it's at the top of its swing, it stops. It's got no kinetic energy, so it's all potential energy. And then as it goes down, the potential energy starts to fall. Our datum point is the lowest point of the swing, where the potential energy would fall to zero, and then it would all be kinetic energy and back up the other side. So kinetic energy and potential energy are swapping places, and kinetic energy, it can be viewed as it can be written like this. A little bit more of an explanation of that as we go down. And we got the wave function of, we're given the wave function of, in this case will be hydrogen. So all we have to do is multiply all of this by the wave function, and the energy of the wave function is this. This is called the Hamiltonian. It's the way the energy changes from place to place. There's your Hamiltonian. Now consider momentum as an operator acting on the wave function. The operator, a little hat over the P here, it's an operator. P squared, we've got your 3 dimensions, so we're momentum in 3 dimensions. The operator in px, the px in the x direction is here, py, and so on. And 3-dimensional Schrödinger equation ends up as this. There's your momentum, your potential, your kinetic momentum. It's kinetic. Here's your potential energy, and it's the total overall energy. It can be written as this, where this is the Laplace operator. It's the same as this. Okay. There it is, time-independent Schrödinger equation. There's a whole lot more information about a particle in a 3-dimensional box here for your information, should you wish to run through that. But that's what we're looking at, the particle in the in a three-dimensional box, which is the three-dimensional potential well that our hydrogen atom is sitting in. And so and we go application of the Schrödinger equation, shoot on to the solution, and so on. So these are the common operators. We see you have there. You have the position is X or Y or Z direction. Momentum in whatever is taken X as its X direction as its as an example. Each of these will have Y and Z direction. Potential energy now is calling U, where it was calling it V. Kinetic energy K. These are the operators operating on the momentum, and the Hamilton is a combination of the two of them. So, and then you have total energy is change across time. Okay, you can have a look at all that for yourself. The approximation of the potential energy of the electron-proton system is electrostatic. Now, this may not make sense if what I'm saying is the electron doesn't actually exist. It doesn't have independent existence. So approximation of potential energy of the electron-proton system is electrostatic. Now I'm saying that instead of this finding the electron, here's your proton, the electrons with it around somewhere or the other. No, I'm saying this is the energy of the proton. Where you're reading it from is going to read here or here or here or here. So it's looking at this distance. That's it. It's just the same. But the electron isn't there. Now, this E is minus E. Now, if I were to say that's the charge of the electron, supposedly, I'll say no. This potential, if we were to integrate that dr, we end up with E squared over 4 pi in R squared. We'd end up with half of E squared. Now what I'm saying is, this is the charge of the proton. Half the charge of the square of the proton divided by the permittivity of free space, because there is a distance across which it's measured. There's your R squared, but this, look at this, 4 pi R squared divided by the area of a sphere. As is spreading out, the proton energy is spreading out across the sphere, and that's what you have here. You have the derivative of the energy across this sphere. How much that energy is changing on that sphere according to r squared. So again, we don't need the electron to describe this. Okay, having that, we rewrite the three-dimensional time-independent Schrödinger equation to this. Okay, there it is. And, excuse me, that's my phone dinghy. I'll put that to silent. So rewrite the time-independent Schrödinger equation, and then so far we've been working in dx, dy, dz, x, y, and z. Now what we want to do is apply the Schrödinger equation, transform to spherical coordinates. Now, if you've studied the Schrödinger equation, if you've studied quantum physics, we're always working in polar coordinates, because we're always talking about the sphere of influence, the energy sphere, the particle as a sphere. So when we rewrite the time-independent Schrödinger equation using spherical polar coordinates, we end up with this. And again, you can have a closer look at that. Just pause it. That's where we get to. Now, the application of the Schrödinger equation, the wave function is a function, of course, the wave is operating in polar coordinates in r, theta and phi. R theta, if I just come back to that for a second. Distance r, and there we have theta. There's a z-axis, theta from here, and phi in this direction. That's it. So the wave is operating in those three coordinates, and so what we can do now the wave function can be written as a product of the three functions. Let's just call it r in the I direction, function f in the theta direction, and g in the phi direction. And that means we can separate the former equation. By the way, that was equation 7.3. Let me write that in there. Where you gone? Yeah. Seven 3. So we can separate 7.3 into three separate coordinates, and substitute 7.4 which is the one we just saw with the 3 coordinates. So separate it into its 3 coordinates. You end up with this. The differential of the wave function in the r direction ends up as this. If you'll know your calculus, you'll understand how that comes about. Substitute this into 7.3, we end up with this, and multiply, that's now 7.6. 7.76. Multiply both sides of that by this, and we end up with this equation 7.7 here. Again, if you want to pause this and have a close look, do. Only r and theta appear on the left side, and only phi appears on the right side of equation 7.7. The left side of the equation cannot change as phi changes. The right side cannot change with either r or theta. So each side needs to be equal to a constant for the equation to be true. Set the constant minus ml squared equal to the right side of equation 7.7. This is called the azimuthal equation. Just let me back to there. The theta direction. These are the polar angles down here. In the phi direction, these are the azimuthal, around. So it's down there and around. Polar, azimuthal. And where did we get to? Oh, here. No, further up. Oh yeah, this is sorry, I jumped on. So d squared g d theta, that's theta there, theta squared equals minus mlg. Just take that one to the next one. E to the I ml theta satisfies the last equation for any value of ml. Goes on to give you some information. Solution has to be single valued. ml must be 0 or an integer. We've seen that before. We know what ml is. It's one of the atomic numbers. Set the left side of equation 7.7 equal to minus LL and rearrange it, and we get this. Everything depends on R on the left side and theta on the right side of this equation. Okay. This is all to do with set each side of the last equation to a constant, L plus 1. We'll have a look further into what L multiplied by L plus 1 is later on. But then we have separated all of this. We have an azimuthal solution we have a radial, an azimuthal equation, a radial equation, and an angular equation. So there are our three second order differential equations: 7, 8, 7, 10, 7, 11. And the radial equation gives you what that's actually called. Assume the ground state has L equals 0, then 710 becomes this. The derivative yields two terms. Write those terms and insert equation 7.1. This has all been done for you. So we end up with this radial equation. Quantum numbers, when L equals n minus 1. So when we have n equals 1, L equals 0. When n equals 2, L equals 0, minus 1 and plus 1, and so on. So L always, when L equals 2, when n equals 2, L equals 0, minus 1, plus 1, minus 2, plus 2, and on it goes. ML is minus L plus 1, and so on. We saw all this in previous videos. We saw this in previous videos. There's nothing we haven't discussed before in that. Let me take that out. And now solution to the radial equation. Now try a solution R equals A to the E to the minus R over A naught. A is a normalization constant. Remember this normalization. It's what you need to ensure that the particle exists and will be located from somewhere. You know, sooner or later, whatever distance, you will have this location happening. A naught is a constant with the dimensions of length. Take the derivatives of R and insert them into 713. We end up with this. To satisfy, this is 714 then. To satisfy 714 for any R is for each of the two expressions in parentheses to be 0. Set the parentheses equal to 0 and solve for A naught, and we can get A naught. Set the first parenthesis equal to 0 and solve for E. E equals minus E. You can follow all this for yourself. This is all leading up to, you've got an example of normalization there. If you want to have a look through integrating a wave function to an infinite radius to give you your normalization function. There's an example. I'm sorry, if you want to have a look at that, then oh no. Yeah, if you want to have a look at that, then pause it, go through it. But there it is. And now this leads us to hydrogen atom wave functions. First few radial wave functions for R at the different energy levels. R at NL, if you can't read that. So n equals 1, L equals 0, we get this, which is 2 over A naught, so that's 2 over A naught to the 3 halves E to the minus R over A naught, and so on. And if you look at each of these, they just depend on A naught has is a constant with distance, and all the variables, the only variable in all this is R, so that as n changes, of course R changes. N1, N2, of course R changes. N2, L0, L1, L2, etc. So that as N and L change for each shell and subshell, then the radius changes. So the only thing that's varying on there is R. Let me take that out. If you want to pause that and, I don't know, maybe magnify it so you can read it. So there it is. That's what we have. That's the result of the Schrödinger equation applied to the hydrogen atom radial wave functions. Then on to the angular and azimuthal equations. So now we're looking at the other two aspects of the polar coordinates. And solutions for 7, 8 are these, and solutions for the angular and azimuthal equations are linked because both have ML. So we can tie them both in together and call it Y. Now that's a wave function depending on the other two polar directions. These are now spherical, the spherical harmonics of the hydrogen, the wave function of the hydrogen atom. And now when we look at this, when L equals 0 and ML equals 0, there we have no angular. This is constant. When we move to L equals 1 and ML equals 0, then we get cos theta involved. When we go to L equals 1, ML equals plus or minus 1, then we get both angles involved. So all we've got here, in effect, is another variation on R. It's a constant. It's varying R. Now we've got the polar direction involved. And now when we get plus or minus 1, we've got the polar and the azimuthal directions involved. So again, if you want to have a closer look at that, please do pause it and magnify it. But I'm going to be coming back to these two and talking talking about the results with respect to what we're looking at. Because when you're looking at all this, quantum mechanics is now saying, you know, it's determining this in polar coordinates, cos theta, e to the minus phi, and so on. So these coordinates are, as it were, plotting orbits, particular orbits. But now quantum mechanics say that there are no orbits. But all of this is predicated on orbits and orbitals. It doesn't really make sense. I want to make more sense of that. I'll be coming back to this and this and discussing much more of what it means. The radial function R and spherical harmonics determine the probability density for the various quantum states. The total wave function depends on L, N, L and ML. The wave function becomes this. Okay. And quantum numbers, again, you can have a look through that. Principal quantum number n. This is all stuff that we've looked at before. The orbital angular momentum quantum number L. Now, the orbital angular momentum, capital L, is a bit different. Remember in one of the results we wrote this in, and this is L. This is the actual angular momentum, and energy levels are degenerate. That means you can have more than one energy level to with respect to L. Of course you can, because let me give you an example. Oops, that's not what I meant. So let me give you an example. If we've got these two, they're at the same energy level. So are these two. It's just their spins are opposite. So these are all degenerate. And you don't know which one you're going to get. So you can read a whole lot more on degeneracy. It's not quite as simple as that. And we have an uncertainty principle for angular momentum, the total angular momentum of the atom. We'll have a much more of a look into that afterwards. Magnetic quantum number. See, you've got an example here. ML is 0, ML is 1, 2, minus 1. This is exactly as I have drawn it. But let me come back to all of this. Now we've got those results. We've seen how we got there. quantum numbers, it'll tell you much more about magnetic quantum, angular momentum components, and fuzziness of angular momentum. What does it mean by fuzziness of angular momentum? Okay, we won't worry about that one right now. So, fuzziness of angular momentum. I want to look at the results from what we've seen of the Schrödinger equation, and what that actually means when it's applied to my definition of the atom, the hydrogen atom. I'm going to have a closer look at that, so I'm going to pick out the results and some of these fuzziness of angular momentum as well, being one of them, and we'll have a closer look and see how all this applies to my model of the hydrogen atom. My model that has no electron involved. And so, following on from that very brief run through, very rapid run through of the time-independent Schrödinger equation, from which we obtained a series of results that we're going to have a look at and see how they apply to my model of the hydrogen atom and the proton, and from that to every atom without the need to include electrons. Before we do that, I just want to have a quick chat about precession. And precession is from this diagram, which is a kind of gyroscope. If we've got the spin of the gyroscope around in this direction, then the gyroscope itself, the thing itself, will spin in this direction. So the spin carries on in this direction, but the angle of the thing itself precesses around like so. And what we're going to do, we'll look at that in terms of a particle. Not an electron, but a proton or a hydrogen atom spinning. There's its spin, and this will be its precession. So I just wanted to make you aware of that, because I don't want to have to describe that as we go through. And when we apply that to the frequency of hydrogen nuclei precession is known as the Lamore frequency. So this is going to apply to our model of the hydrogen atom, and thereafter every atom. our next step then is to, now we've achieved those results from the Schrödinger equation. We want to see how they apply to the hydrogen atom, to the proton, and from there to every atom. To do this, to start off with, I'm going to come back to this diagram for the neon atom, with its the accepted view of this is the neon atom has 10 neutrons, 10 protons, so this supposedly depicts the electrons in orbitals, whatever they mean, around the nucleus. And I would say no. This whole thing is the nucleus, and what we have is 10 neutrons, and these are the 10 protons at different energy levels or different spins. They could be at the same energy level, but they'd have to be at the opposite spins. Okay. This just a very quick recap then, because what I'm going to have a look at is these energy levels. N equals 1, these different shells, N equals 2, and so on. So let me just quick run over that again. Sorry, it's all marked up and grubby, but we can still see what we want from it. So N, principal quantum number, the shells and subshells, N equals 1, 2, 3, 4, etc. L, orbital angular momentum, which is really what we're going to be interested in. L, when N equals 1, L equals 0, and we'll have a look at that underneath that. And ML, the magnetic quantum number. Magnetic quantum number, let's say. The boundary conditions, N equals 1, 2, 3, 4, L equals 0, 1, 2, 3, N equals 1. It's always N equals 1. But when N equals 1, L equals 0. When N equals 2, L equals 0, 1. The 0, 1. When N equals 3, L equals 0, 1, 2, 3. And then ML, when L equals 0, the books say ML equals 0. I would say when L equals 0, ML is irrelevant. There is no ML. When L equals 1, ML equals minus 1, 0, plus 1, and so on. So how did that apply to our neon? N equals 1, L equals 0. This is the L equals 0 line. It's, remember, ML is the magnetic quantum number. These line up. Let's say this is north and south. North and south positive and negative spin, these line up on this axis. So these first two, when n equals 1, L equals 0, there is no ML, they just line up here, the two of them. Spin up, spin down, opposite spins. That's it. They're at the same energy level with opposite spins. And we went into that and discussed exactly what that meant. But we're there when L equals n equals 2, L equals 0 again, and these line up in the next shell. So the radius is increased, but they're in this shell. Two opposite protons in this shell, spin up and spin down. These ml equals -1. Now L, this is L equals 0. Now we have L equals 1, ml equals -1, 0 plus 1. And a similar thing, plus 1, but opposite spins. Okay, that's it. What does this mean in terms of, what does it actually mean? It's all to do with the energy related to angular momentum. What we're interested in is angular momentum. Spin angular momentum is one thing. They all have their spins. Okay, now we're looking at orbital angular momentum. And before we move on to what that means, what I'm doing here is, forget this is neon. I'm using this to call this a hydrogen atom, and it only has the one proton. Now, what these are now signifying are the possible energy levels for that proton, for that single proton. It's the same as the neon. This proton, the single proton in hydrogen, could be at any of these energy levels. And if we gave it even more energy, it would move out to the next level, and then the next, and then the next, until we gave it 13.6 eV, at which time it would be ionized, so it would make contact with the outside world. It escapes the potential well. So this is a good illustration of a hydrogen atom and the possible energy levels of its single proton. Okay, so before we move on, let me go back. Not that one. This one. Nope. Where am I? Here. Remember what we did when looking at the Schrödinger equation. We have the Z, the Y, and the x-axis, but because of the spherical nature of any proton, we used spherical polar coordinates. So we have the 3 coordinates, which would be just the radius, how far out, effectively how far out the proton is, effectively how energetic it is. So we have this element, and then we have its other elements of orbital momentum. The polar coordinate moving from around the z-axis, from the z-axis down back to the z-axis, which is theta, and then the azimuthal element that moves around, which is phi. So take that. Now, remember when we applied the spherical coordinates, we ended up with this Schrödinger equation, which gave us our set of results. And I'm going to then, remember this is now our model of the hydrogen atom and the possible positions for N1 and N2 in the hydrogen atom. And I'm going to see how our results for the hydrogen atom can apply to this model. Now, first of all, we have the radial wave functions, and if we look at these, when n equals 1, L equals 0, there we have this radial function, which I don't know if you can see that, it's a bit small, so I'll write that 2 over a naught to the 3/2 times e to the minus r over a naught. A naught is a constant with units of distance, so the only variable we have is r. And if we look at when n equals 2, L equals 0 or L equals 1, all the way through these are increases, but there's only r involved. There's no other variable because it's radial. That's exactly what you'd expect. So just let me return to here. As we go from, as we go from n equals 1 to n equals 2, the radius changes. This radius changes. And once we're out of this radius at n equals 2, then we have these other energy functions. I'll have a look at what they are. So that much is simple. What we gleaned from the Schrödinger equation, that of course as the energy increases, so does the radius. This is what this is showing. Now, if we come back to now normalized, we went into what normalization actually means, but these are normalized spherical harmonics. Now, if you look at this, when L equals 0, I would say ML is irrelevant. But when L equals 0, the spherical harmonics is just 1 over the root 2 times the root of pi. It's a constant. There's no polar angle or azimuthal angle. All it is the is a constant. So when L equals 0, whenever L equals 0, the spherical harmonic is a constant with no polar or azimuthal component. Come back down to here. Let me take that off. Then, of course, what I said was this line's up here. It's moving up and down this north-south. And that's all that's happening. So that, don't forget, this is the same proton in the hydrogen atom. It's just shifting along this line. In actual fact, I would say it's not shifting at all. All that's happening is it's at this energy level, and if you approach it, if you catch it here, if you're coming in from here, you'll get spin up. If you look at the same thing from here, you'll get spin down. That's all. It's the same. It's the same thing. It's the same proton. And a similar thing when we give it some energy and it moves out to n equals 2, then we still get L equals 1, and it's on this same. So it's not. There's no orbital angular momentum involved when L equals 0, and you're just going to look at the same thing from one side to another or another, and you're going to see it as spin up or spin down. That's it. Now, take it back to here. Now, when L equals 1, ML equals 0, now we have cos theta. If you can see that, that's half divided by 3 over pi, all a constant, but then cos theta. Now we have a polar element. How do we have a polar element? Come back to here. And these are all our L equals 0s, but now we have L equals 1. So ML equals 0. They say ML equals 0 for this as well. I say no, it's just L equals 0. There's no ML function. And when ML equals 0, what it means is that this proton is now revolving in this direction. Polar. It's polar element. It's revolving. It still has its spin, but it's revolving around here. So it's spin, spin, spin. Around it goes. So that its wave function has this, it's moving down here, it has this theta element. That's this one. So it's just, it's actually spinning round here. It's at this extra energy level, but now it's spinning round. And it won't spin round, you can't tell whether it's spinning round, say this is our Z, this is X and this is Y. You can't tell if it's spinning like in the ZY or ZX. And in fact, when it makes its journey from around here, then although it's doing it, it's a polar journey, it may not necessarily take the same route. So if you're actually looking at what all this is looking at now is L, the angular momentum, orbital angular momentum. So this has now orbital angular momentum. It has none when it's in here. As we said, there's just a difference in radius. Now we have orbital angular momentum, but still in the Lx direction. Lx equals 0. Now we can't know what Ly and Lz are because of the uncertainty principle. It won't allow us to do that. But of course we don't know. We don't know what route that's taking around there, and then it may change that and change that. It's not so that the change in Ly and Lz is not determined. We can't determine what that is until we fix it by measuring it. That's it. That's the uncertainty principle. Now, come back to here. And now, when L is plus or minus 1, and now we have plus or minus, if I can write this out somewhere, a half, plus or minus a half 3 over 2 pi sine theta. So we've still got our polar coordinate, but now we've got e to the plus or minus I theta. Now we have an azimuthal element involved. And let me tell you what they are there, and you will see repeated down here every time. If L equals 0, there is no orbital angular momentum. When L equals 1, ml ml equals 0. We have this when L equals 1 and ml equals plus or minus 1. Now we have azimuthal, and that will be repeated all the way through. When L equals 2, ml equals 0. Look at that. ml equals 0. We only have the polar element. When ml equals plus or minus 1, then we have the polar and the azimuthal, and ml equals minus 2, again we have polar and azimuthal. That all makes sense now. Look at this. Now we have here L equals 0 for both of these. For all of these, L equals 0. And that's it. They're just on this plane. Now, when L equals 1, ml equals 0, ml equals minus 1, sorry, ml equals plus 1. Now, ml equals 0 means that it is revolving in this direction. Effectively, orbital angular momentum in the polar direction. Now, if we now shift the axis to here, we still got this orbit, but now the orbit axis is shifted, and because it's shifted, now we get the azimuthal element that was depicted here. Now, look at this. This is exactly what we have. We have now, there's the orbit, there's the shift that the orbit will make. And so now when we look back at this again, sorry, this again, we have the azimuthal element across here. So this is still taking this angular, polar angular, and it's tilted it. So the whole thing, this plane has been tilted here. And because this is now on the tilt, it will shift around here. So this is going to shift. So getting a bit messy here. Let me take this out. Getting a bit excited with this. So for this, we've got this. For here, we've got this still, but now it's at this angle. And what it will do is shift around here. This is why we have the polar and the azimuthal directions to this energy. And the Schrödinger equation applied to this model of the hydrogen atom with its protons in these positions. Those results from the Schrödinger equation tell you exactly what that wave function will look like when we're in ml equals 1 or ml equals 0 at this energy level. That's what it's saying. That's what it's showing. And just to finish, if I can go back and say that when you apply that to the convention that these are electrons, it doesn't make sense, because the electron is neither here nor there. It's in a cloud. It's in a superposition of states. So when you read all this, it says, these are the results, these are the wave functions, and so on, and then it applies to your electrons, but then electrons don't really have this. How can that make sense? It doesn't make sense. It makes sense when what we have are the protons, or the proton. At different energy levels, and now the wave function makes sense. It has these different elements to it, and if this proton is shifting around here and the angle of that is shifting around here, remember, when you've got a proton, you're going to make a measurement with it, but it is a sphere of influence. So it might be here, it might be here, it might be here. You don't only communicate with it here. You can, but you can also measure it here and here and so on. So it's fuzzy where it is, even if it was stationary, which it certainly isn't. It's moving around here. You can't tell where it's going to be at any one time. And from what position are you approaching it? All these things are unknown. They're uncertainties. So we have an explanation for the uncertainty principle. You can't know any of these things until you pin them down. Nothing is determined until you pin it down. But now we see that the results from Schrödinger actually make sense. They do apply to the possible positions and the energy levels of a particular proton. Of a single proton in the hydrogen atom. And I would say then, if we take this back to neon, and this nucleus is just the neutrons, this is a model of the whole nucleus, then if this is neon, then, and it is at its ground state, then all these are filled. That's it. But if we and each of these elements has its wave function. Now if we shift this one out to here, now we have the atom in an excited state. Now you don't know where that's going to be. It could be on this line, it could be excited out to any one of the possible states that exist in the next shell and its subshells. So you can't tell where it's going to be until you pin it down. So that's it. It's uncertain. It has all these possible wave functions, and when you locate it, you would then, in reading this excited proton, in reading its excitement, you would take away the energy and it would fall back to its previous position. There it is. So I am going to do another little video on the measurement problem. See, won't let me clean it up any more than that. If I put too many dirty marks on this software, it has enough. It won't let me go back to where I was. But never mind. We've covered it. So to summarise, we're not ever looking at electrons. We're only looking at protons and their energy levels, and their energy levels depicted by an increase. If one increases its energy level on this, increasing level on this path, so it's not an increase in orbital angular momentum. What is it then? It's spinning. It's going to spin faster, isn't it? It's going to spin faster, and you know it get more frequent, more energy it gets more frequent, so it's spinning faster. That's it. And now, when you bring it out to here and it's spinning faster, you can give it a little bit more energy by spinning it in this direction, which is your polar element. And then you can alter the angle of that polar spin and make it revolve in the azimuthal direction. That's it. That's all I'm saying. So again, I'm able to describe exactly what's happening at a quantum level without subatomic particles. All we have to do this are protons and neutrons. And as I've said before, the neutron is just a proton with a bit of a change of energy. If you isolate a neutron, it only has minutes to survive as a neutron and change back into a proton. So there it is. I'm going to produce a small, a very brief video on the measurement problem next, and then I don't know what comes after that, but what I'm leading up to is to showing that there are no subatomic particles. None. This is a bold claim, I know, but I'm going to keep on going with these descriptions and show that everything can be described without reverting to subatomic particles. Okay, that's it. I hope you'll join me in the next video, which will be a short one, I promise. Measurement problem. I'll hopefully see you there. Bye bye.